Our first implementation of a data structure for union find is going to be a linked list implementation. Each of these two linked lists correspond to our two disjoint sets. So each linked list is a set. Just so we can understand the way I've drawn these linked lists, the head of the linked list is this node x1 over here, which I've signified by giving it the sort of double lines around it. So x1 and x6 are the representatives for those sets, and we have a header pointer. This is our head pointer that says where we start, and every single node has a next and a previous pointer. So if we're talking about this, we'd have a linked list node class, which will have a pointer to the next and a pointer to the previous and some data stored. And if you're familiar with linked lists, you'll know we can make this much more efficient in a particular way, because if I wanted to, from x5, determine what is the set that it is in. If I want to be consistent about this, the most obvious way would be to just go to the head of the list. So I need to follow this bottom edge, then this bottom edge, then this bottom edge, then this bottom edge, all the way to x1. And that seems like it could be really inefficient. One useful trick for improving the efficiency of a linked list is to add one more set of data to the linked list node, and that set of data is going to be a head pointer, which will always point at the head of the linked list. So that is one other bit of data we're going to store. And for our purposes, if the head of the linked list containing a vertex matches with the head of the linked list containing another vertex, for example, x5 and x3 both have a head node of x1, therefore they're in the same set. And if I instead compared, for example, x4 and x10, they have a different representative. x4 has a different representative, which is x1, than x10, which is a representative of x6. So they are in different sets. So that is going to be the way we are going to determine what sets these are in. So first, let's look at our smarter implementation of a linked list. It looks a lot busier, but it's not so bad. Every single node, including the head node, has a pointer to the head node. So all of these lines on the top are just the pointers to the head node. And the head node also has a pointer that points all the way back to the tail. Now, with this understanding, let's look at the code for how we implement our functions via these linked lists. So let's go down. Find set is very easy with that implementation. All I need to do is return x.head. This is easy to analyze. This has a constant runtime, because it's just returning the whatever's at a certain pointer. Totally trivial to implement. That's nice and easy. How about union? Let's look at the way this works. Step 1, we find x prime, which is the representative for the set x. So here, x prime would be x1 if I'm assuming that this first list contains whatever node x. Let's suppose, for example, that x4 is x and that y2 is y. So we've written that over top just to make sure we understand what we're doing. So x prime would be x1. I'm not going to write that over top just because it gets a bit messy. And y prime would be y1. So if we're going to union these together, we're going to first take x.tail.next and make it y prime. So we go to x.xprime.tail, so x1, tail, and then we're making its next pointer point at y prime. So we're going to draw in an arrow pointing down there to y prime. And then we're going to start at y prime. And what are we going to do? We're going to loop until we find null. And we are going to set the head pointer to point at x prime. So, doing this, we're going to add in a bunch more pointers from here that point up to x prime, all of those being the head pointers that previously pointed at y prime. And then afterwards, we're going to make the x prime dot tail point at y prime dot tail. Now, let's look at what we have. We have, if I highlight this accordingly, I'm going to be assigning these head pointers. I'll highlight that in blue. I'm going to be assigning the tail pointer its next value. That's what I did in black. And I'm going to be assigning the tail pointer of x prime to be whatever the previous tail pointer for y prime was. So that's the stuff I did in purple. So that's how this method works. You take the first linked list and add the other one onto the end. So that afterwards, this linked list would look like x1, x2, x3, x4, x5, y1, y2, y3, y4, in that order, with the pointers pointing both directions between every single set of nodes, and a bunch of header pointers I'm not going to draw in, pointing at x1, and one long tail pointer pointing back at y4. So I'd have all of this information all stored in one long list. It's tedious to draw, so I'm not going to draw it. So I just kind of drew it in this horrible mess of colors over there. But that is the way union works. You might notice that we didn't do anything intelligent here, and we have a loop. And we have decisions we could make. If I wanted, I could look at these two lists, and I need to loop over one of them. In this case, I'm looping over the second argument. Instead of doing this with no information, why not always loop over the smaller of the two lists? We're going to have to loop over a list to connect all of the pointers back up, but why not loop over the smaller of the two? So our more intelligent way of implementing this, we're going to call union weighted union, which we'll come back to make a set out of something. I should mention this, again, really straightforward. We make the header pointer point at x, we make its tail pointer point at itself, and its next points at nothing. So set a set of the pointers, that's what we're doing there. For weighted union, this code will look very similar, but with a bit more intelligence behind it. We find the representatives again. If they're in the same set, we don't need to union them, we're done. If x is larger than y, that's our case we had up here actually. If x prime's list is longer than y prime's list, then we're going to want to loop over the y prime list. Because it's smaller, we want to loop over the smaller list. So this code is exactly the same as the code we had before. But notice we have something we've added here. X prime.length and y prime.length. We have to increase our storage a little bit to actually do this in a clever way. So we're going to be storing the length of the linked lists and updating that length accordingly when we need to by just storing that bit of additional information. So if we have n elements we're storing in these disjoint sets, we're going to have n additional data storage to store this length. So this doesn't come for free to get some additional runtime benefits. As always, we're paying a bit of a price in terms of storage to gain this runtime benefit. And then this code is identical except for this line here. And then if x prime.length is not greater than or equal to y prime.length, then x prime will be the smaller of the two lists, in which case, and this is the way to be really clever with programming, all I need to do is swap the arguments. If I swap which one is x and y, then it's all set, right? So if we look at this list here, let's suppose that I actually called this y, the first one, and this x. In this case, y prime.length would be 5, and x prime.length would be 4, and we would say, okay, we do not enter this if statement, we do not enter the if statement, we enter this if statement, and we swap which one is x and y. And now we're in the exact same scenario as before, where we're going to make x prime.tail is going to point there. We're going to make all of these point at x1 as their head. And we are going to make x5.next point at y1. Huge mess. If you're doing this on your own, you're going to want to redraw these pictures and draw them in a sequential order to make it a more sane thing to look at. But for our purposes, this is enough. We are always going to make all of the elements in the smaller list for weighted union point at the head of the larger list. That's all of these arrows going up there. We're going to make the tail pointer from the first list point at the last element of the smaller list, and we need to make sure to attach the end of the bigger list to the start of the smaller list. So that we need to make sure to get all of these pointers pointing in the right direction. And as I'm sure anyone who's worked with linked lists has encountered before, you need to be very careful with the pointers to make sure you do this. Drawing the pictures will always help you whenever you need to analyze code like this. The runtime for this is going to be a bit tricky, so we'll save that for the next video, but these are our methods for our linked list implementation of Union Find.